All right, in this section, we're going to see why polar form is so helpful. It makes certain calculations so much easier to do. In fact, it's multiplication, division, raising numbers to powers, and finding roots of complex numbers become really totally doable if we use polar form. So I'm going to start out with a couple of arbitrary complex numbers in their polar form. I am purposefully using the exponential form because it's what's going to help us figure out how this all works. We're going to be able to use our properties of exponents here. So I'm multiplying these together. Now, the first number, r1 times e to the j theta 1, that's also a product. We're just multiplying a bunch of things together. I can rearrange this product in any order I want. So what I'm going to do is group the two r factors in front, r1 times r2, times, and then the e raised to the power factors at the end. So e to the j theta 1 times e to the j theta 2. This is equal to r1 times r2. Now, when we think about multiplying these here together, I have the same base, right? And I'm multiplying them together. Our rules of exponents tell us that we can add the exponents. And inside the exponent there, now we have a common factor of j, so I'm going to factor it out. And there's our product. If we did this in trigonometric form, it would translate into this product being equal to r1 times r2 times cosine theta 1 plus theta 2 plus j sine theta 1 plus theta 2. The upshot of this is that if we are multiplying two complex numbers in polar form, we're going to multiply the two moduli, those magnitudes, the r values, and then add the angles. When we add the angles, we have to make sure that we're giving a standard position angle between 0 and 360, or between 0 and 2 pi if we're in radians. And we'll see an example where sometimes we have to do a little extra work to make sure that our angle is within the bounds that we need them to be. So let's begin. Here they're asking us to find a product. These two numbers are given to us in polar form. Look how little room I left for us to do this is because it's going to be simple. What we just derived up there is the fact that all we need to do is multiply the two r values, so 3 times 2, and then add the angles. 70 degrees plus 55 degrees. This gives us 6 at an angle of 125 degrees. Now let's think about division. Suppose I want to divide a couple of complex numbers. They just have these two arbitrary ones like we did with the multiplication on the last page. I'm going to split up this fraction as a product of two fractions. I'm going to segregate out the r values, so we have r1 over r2. I'm going to multiply by e to the j theta 1 divided by e to the j theta 2. Got my quotient r1 over r2. Now, when we're dividing with the same base, we get to subtract the exponents. So this is e to the j theta 1 minus j theta 2. Or in the exponent, now I have that common factor of j, so I'm going to factor that out. So we end up with r1 over r2 times e to the j theta 1 minus theta 2. We could see why this is true using that exponential form. Kind of gives us a lot of insight into how we do this. Now, if we look at how this looks in the trigonometric form, this will look like r1 over r2 times cosine theta 1 minus theta 2 plus j sine theta 1 minus theta 2. The upshot of this, what we can observe, is that if I am dividing two complex numbers that are in polar form, we simply divide the moduli, those r values, and then subtract the angles. Again, making sure that our angle at the end is a standard position angle between 0 and 360 degrees, or 0 and 2 pi radians. So let's do this division. They've given us the numbers in polar form. So let's see. We're going to divide the two r values. So 2 over 3, and then cosine 55 minus 70 plus j sine 55 minus 70 cosine of 55 minus 70 is negative 15 degrees. So here's where I'm not quite done yet, because our angle is not between 0 and 360. So my angle is negative 15 degrees. That's like starting at the positive x and going down 15 degrees. I just want the standard position angle. So that negative 15 degrees, I'm just going to add 360 to it. And that gives us 345 degrees. Okay. Let's try another. Here they're giving us a couple of complex numbers in rectangular form. They want us to multiply, but they want us to do it by first converting each to polar form. So let's do the conversions. So let's work with 2 plus 3j first. 2 plus 3j is in the first quadrant. R is the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9, or the square root of 13. And theta, it's in the first quadrant, so it's just going to be arctan of 3 over 2. And I think I'll go ahead and put myself in degree mode. You could be in radian mode if you like. 56.3 degrees. So 2 plus 3j is root 13 at 56.3 degrees. We'll do the same thing for 1 minus j. Now 1 minus j is in the fourth quadrant. So let's see, r is the square root of 1 squared plus squared. R is the square root of 2. And theta, if it's in the fourth quadrant, is going to be 360 minus arctan of 1 over 1. So just arctan of 1. Arctan of 1 is 45 degrees, so that'll be 315 degrees here. And that means that 1 minus j is equal to root 2 at 315 degrees. So now if I'm finding this product, this is root 13 at 56.3 degrees times root 2 at an angle of 315 degrees. I'm going to multiply the two r values and then add the angles. Root 13 times root 2 is root 26, which is already simplified as a radical. 56.3 plus 315 is 371.3. Too big. That angle is too big. It's outside the range of 0 to 360. So we're going to subtract 360. We're subtracting 360 because we're just sort of going back one full revolution. We'll end up in the same location in the plane, which is why we're allowed to do this without changing the value of the number. So if I subtract 360, that's 11.3 degrees. Okay, so now we're going to do the same thing with these numbers, or we're working with the same numbers, only this time we're going to divide. 2 plus 3j, this was root 13 at 56.3 degrees. 1 minus j is root 2 at 315 degrees. Just double checking those. Yeah, okay. And so when I divide, I'm going to take root 13 over root 2 at an angle of whatever we get when we subtract. I'm going to do a couple of things here. First of all, the root 13 over root 2, I'm going to just rationalize that fraction by multiplying top and bottom by root 2. So then we get root 26 divided by 2. And this angle, 56.3 minus 315, is negative 258.7. Negative, which is not in our range, right? So we're going to add 360. And that'll get us a nice standard position angle. .3. As we've seen here, the polar form can be really pretty convenient for multiplying and dividing. If you need to add and subtract complex numbers, you've got to do that using rectangular form. So if you were starting with rectangular form, you wouldn't convert to polar. And if you were starting with polar form and needed to add or subtract, the first thing you would do is convert to rectangular form, so you can add the real parts and add the imaginary parts. Alright, so now we're going to move on to other operations. We're going to look at powers and roots, and we'll begin with a pretty powerful theorem. De Moivre's theorem tells us that if I want to raise a complex number in polar form to a power, we're going to just raise the modulus to that power, right, like we see here, and multiply the angle by that power, right? So instead of theta, I've got n times theta in the exponent there. It's pretty, it's kind of simple-ish to see why that's true when you use the exponential form, right? We're just using our properties of exponents. And in fact, we actually kind of saw this at the end of, or near the end of, the last section. Right, so we did this problem where we were raising a number to the third power, and we just used our rules of exponents. So as it turns out, we just raised r to the third power and multiplied the angle by 3. And that's what De Moivre's theorem says that we can always do. So let's raise 2 plus 3j to the third power, and we're going to do that by first finding the polar form. So 2 plus 3j is in the first quadrant. And in fact, did we already? Yeah, we already found that, right? That's root 13 at an angle of 56.3 degrees. And we're going to raise this to the third power. So I just need to take r to that power. So root 13 cubed, and then multiply the angle by the power. Root 13 cubed is 13 times root 13, and if we multiply 56.3 by 3, we get 168.9. Now they did say we're not quite done. They said express the result in rectangular form. So I'm going to find 13 root 13 cosine 168.9 degrees plus 13 root 13 sine 168.9 degrees times j. That's 46.9 plus Oh, I didn't multiply. Hold on. Root 13 times cosine of 168.9. Negative 45.995. I'll call that negative 46.0. And then root 13 times sine 168.9 is 9.024, so maybe 9.02 J. Now this should jive when we think about this as a number. We found that its angle is at 168.9 degrees, and we did in fact get a number that is in the second quadrant, negative real, positive, positive imaginary, and that's what the 168.9 degrees, where that should be. We can use de Moivre's theorem to find roots of complex numbers. So, you know, taking a root is just raising to a fraction power. De Moivre's theorem still applies. As it turns out, every complex number, including the real numbers, right, because the reals are included in the complex numbers, has nth roots. So there are always 2 square roots of every complex number. There are 3 cube roots. There are 4 fourth roots. There are 23 23rd roots. To find the nth roots of a complex number, the first thing we need to do is express it in polar form, and then we write the root as a rational exponent. So let's say we want to find the cube roots of j. Now we know there are going to be 3 of them. There are going to be 3 cube roots of every complex number. So the first thing I'm going to do here is write j as in polar form. So j is just positive j, that's in the positive imaginary axis. So j is let's see, the r value is 1 at an angle of 90 degrees. Okay, so now the cube root of j. We're going to find the first root, which we call the principal root. This is, the cube root of j is going to be 1 at an angle of 90 degrees to the 1/3 power. The cube root is a 1/3 power. De Moivre's theorem says I'm going to take 1 to the 1/3 power and then multiply the exponent by the power, 1/3 times 90 degrees. So the cube root of 1 is 1 at an angle of 30 degrees. This is the principal root. The principal cube root. We could find the rectangular form if we like. So this would be 1 cosine 30 plus j sine 30. Cosine 30, I think, is root 3 over 2. Plus sine 30 is a half, so 1/2 j. So there it is in polar and rectangular form. Now to get the other roots, what we have to understand is that when we find these roots, they're all going to have the same modulus. So the principal root had a modulus of 1, the other 2 are going to have a modulus of 1. And what they are is like these cube roots are going to be spaced out evenly around a circle of radius 1. Radius 1 because that's the modulus of the principal root. To find the other ones, we're just going to add 1/3 of a rotation. 1/3 of a rotation because it's the cube root. So we're just going to keep adding. We're at this step here. To find the other roots, add 360 over n to the angle of the principal root, and then keeping the magnitude the same. So for the second root, this is 1 at an angle of 30 plus 360 over 3. 30 plus 120 is 150. So there's the second root. And if we like, we could find the rectangular part. And this will be negative root 3 over 2 plus 1/2 j. And then the third root, I'm going to take the previous angle and add 120 again. So 120 plus 150 is 270. We don't really need to write the trigonometric form to figure out where that is, because at 270 we are at, let's see, 270, that's straight down, so that's actually negative j. So these are the 3 cube roots. And we can visualize them on the plane. We'll sort of see, and in fact, I'm gonna do just jump to another page to draw this out. Okay. So our first one was at 30 degrees. Our other one was at 150 degrees. And then our last one, our third one, was down here at 270 degrees. And so they're sort of equally spaced around. It looks kind of like a flux capacitor, but these are the 3 cube roots of J. Oops. Okay. Let's try one more. We're going to find the roots of the equation. Finding the roots of an equation always means finding the solution, finding where it's equal to 0. So when we want to find the roots of this equation, we're just going to solve x to the 6 minus 64 equals 0. And, you know, we could rewrite it. It'll take just the tiniest bit of algebra. This means x to the 6 is equal to 64. And so just to reword this, this means that if we want to find all roots of this equation, there's going to be 6 of them, right? Because what we're looking for are the sixth roots of 64. Every number, every complex number has six sixth roots. So we start. We're going to write 64 in its polar form, which takes very little work. It's a positive real, so its angle is 0 degrees. Its magnitude is 64. So to find the first root, the 6th root of 64 is 64 at an angle of 0 degrees to the 1/6 power. So 64 to the 1/6 power, or the 6th root of 64, I think that's 2. I'm going to double check. 2. And of course 1/6 times 0 is 0. Now, as a rectangular number, this is just equal to 2, right? So this is the principal root, and it's the one we expected to find, right? We would expect to find 2 to be a 6th root of 64. There's the principal root. For the other 5 roots, I'm just going to keep the modulus the same. The modulus is going to be 2 for all of them, and I'm changing the angle. I'm changing the angle by adding 360 over 6 to each, just over and over again. So our second root (360 over 6) is 60 degrees. Our third root again, I'm just going to add 60 degrees again. Get 2 at 120 degrees. Add 60 degrees again to get the fourth root. To get the fifth root. (180 plus 60 is 240). And then our sixth root is 300 degrees. So we have the polar form of all these roots. We can get the rectangular form just by plugging in, finding those, basically the components of the number, r cosine and r sine. So 2 times cosine 60, let's see, cosine of 60 is a convenient number, cosine of 60 is a half, so that's going to be 2. So 2 times half is 1 plus sine of 60 is root 3 over 2, and I'm going to multiply that by 2 as well to get root 3. So j root 3. At 120, cosine is negative a half, and sine is root 3, positive root 3 over 2. So when I multiply that by 2, I get negative 1 plus j root 3. At 180 degrees, 2 at 180, that's going to be negative 2, right? We can visualize that. 180 degrees is the negative real axis. And that's the other root we expected to find. We would expect to find 2 sixth roots in the reals, right? Within the real numbers, 64 has 2 sixth root, 2 and negative 2. Within the complex numbers, it has all these others. At 240, cosine is negative a half and sine is negative root 3 over 2, and again I'm multiplying both of those by 2, so I'm going to clear those denominators. So that's negative 1 minus j root 3. And at 300 degrees, cosine is a half and sine is negative root 3 over 2. So when I multiply those by 2, I get 1 minus j root 3. And we can see them as just being equally spaced around a circle, right? Because it's 60 degrees in between each one. They have to be nice, equally spaced. If I just kept going, if I got really excited and forgot to stop at the 6th root and said, okay, let's find the 7th root, what I'll get to is 2 at an angle of 360, which is the same as 0 degrees. It brings me back to that principal root. So they're kind of in a cycle. Okay. All right, so that finishes up this chapter. Please spend some time on these exercises and be in touch with questions. I look forward to hearing from you.